Okay, let's get started. We are approaching the end of the semester here. We're working our way through this last section on evolving bodies and brains. One of the things that distinguishes evolution from learning is that we can broaden evolution's reach and allow it to sculpt not just the neural controllers of our robots, but the body plans themselves. We looked at the first attempt last week, Carl Simms's approach. We're going to finish our discussion today of a different genotype to phenotype mapping, which uses Lindenmayer systems. Both the L system robots and the genotype to phenotype mapping that Carl Sims used biased evolutionary search towards certain kinds of body plans, or at least body plans that had certain desirable properties. And those properties were? Symmetry, hierarchy, and fractal structure, right? All three features are things that are ubiquitous in biological systems, plants and animals, and so on. Okay, so in 24 and 25, we've been looking at sort of the nuts and bolts of how you actually do this. Today, we're going to spend most of our time on lecture 26 when we're going to look at not just how to do it, but why would you do it? Why not just design a robot and then evolve controllers for it? Why allow evolution to change the way, to change the body of the robot? Okay, and you're all continuing on with final projects. Been a number of questions about changing your milestones. If you change your milestones, that's perfectly fine. What we're looking for in these weekly reports is that the milestones involve more than an hour's work. So if it's sort of a trivial milestone, you can expand your milestone and put some of the functionality from later milestones into the milestone that you're working on at the moment. Okay, any other questions about final projects? No. Okay, so back to lecture 25, where we were looking at applying Lindenmayer systems to evolve bodies and brains of robots. I introduced you to turtle graphics last time. We then looked at production rules, and a Lindenmayer system then combines turtle graphics with the production rule, where the final sentence that's output by a formal grammar is treated as a string of commands to a turtle, and the turtle can either deposit ink onto a page, or it can deposit body parts into a physics engine, or a turtle can deposit neurons and synapses as it goes, right? So in the Lindenmayer system applied to robotics that we looked at last time, we were thinking about, the easiest way to think about this is that there are two turtles, and both turtles are moving from left to right along a string of characters that has been produced by a set of production rules, and some of those symbols in the sentence tell the body turtle what to do, and other symbols tell the brain turtle what to do. Right? So the two turtles are building body and brain, and they're communicating with one another from time to time. They will sometimes, the brain turtle will connect a neuron or connect the output of a neuron to a joint, and the output of that neuron will then modulate the frequency or the oscillation at that motorized joint. It will speed up the frequency or slow it down. Okay. We ended last time by looking at a few of these Lindenmayer system robots in action. And again, we can see examples of hierarchy and symmetry. And can't really see too much fractal structure in here, but if we were to build these robots bigger, you probably could. Okay. So, one of the nice things about this approach is that it actually provides a nice comparison between a genotype-phenotype mapping that was designed to favor symmetry, hierarchy, and fractals, which is the solid line here. And again, like we've seen many times before, we have an average fitness curve here. I think actually this is a curve from a single run. So we have evolutionary time measured in generations along the horizontal axis, and the fitness of the best robot in the population at that time, which seems to be much higher for the generative genotype to phenotype mapping, compared to, in the dotted line case here, a non-generative genotype to phenotype mapping, where now they were evolving not production rules that took a starting sentence and produced a final sentence, but instead they were just evolving strings of symbols. So in this case, the non-generative encoding is a simpler genotype to phenotype mapping where they're evolving lists of arbitrary length, and those lists can be made up of these symbols and these symbols. Make sense? Okay. It turns out if you do that, that non-generative encoding tends to produce robots that don't have any obvious symmetry or hierarchy or fractal nature. And if you evolve this simpler genotype to phenotype mapping, evolution has a much harder time. So if you remember back to our theme a few weeks back about open challenges in the field of evolutionary robotics, this is one of them, right? How do we design a genotype to phenotype mapping? Or more generally speaking, how do you create a good evolutionary system that is evolvable, meaning you're making it easier for evolution through slight random changes, through mutation and crossover, to continually produce robots that have higher and higher fitness, right? So here are two different evolutionary simulations, or two different genotype to phenotype mappings. They have exactly the same fitness function. They build robots using the same set of construction commands, but one evolutionary system does much better than the other. So this seems to suggest that whatever this genotype to phenotype mapping is doing, and one of the things that it's doing is biasing search towards symmetry, hierarchy, and fractal structure. It seems to be useful. Now, this isn't direct evidence that symmetry and hierarchy and fractal structures are what's allowing one evolutionary simulation to do better than the other, but it's sort of indirect evidence. Okay, let's think about this non-generative mapping for a second, which is just evolving strings composed of these commands and these commands. Is this a direct or indirect genotype to phenotype mapping? And how do we distinguish between those two kinds of mappings?
It's indirect because a small change could change several of the aspects of the phenotype.
That's true, right? So any one change to a string made up of these commands may have a relatively large impact on the phenotype. The hallmark of an indirect genotype to phenotype mapping is that you can change just one number or just one element in the genotype, and it's going to have an impact on more than one phenotypic trait or one part of the robot in our case, right? So, for example, let's see here. Here we go. So remember that one of the commands is a pair of curly braces, and at the end of the closing curly brace is an integer which says repeat the construction commands that are inside this curly brace. So a mutation that changes this integer is going to have a big impact on the phenotype, right? You might have a hexapod which is made up of 3 body segments, and if that n equals 3, corresponding to those 3 body segments, and that changes that number to 2 or 4, you're going to get a quadruped or an octoped, right? Making relatively large changes to the body. So these are both indirect genotype to phenotype mappings, but clearly there are certain genotype to phenotype mappings out there that do much better than others. Okay. That concludes our discussion of Lindenmayer systems. Any questions about this one before we move on? Okay, so let's change gears now. Now we're going to switch from how to go about evolving bodies and brains to why we might want to do so. Okay. So the lecture for today is drawn, the material for the lecture for today is drawn from some work I did a few years ago on what has since become known, sort of somewhat tongue-in-cheek, as Evo-Devo Robo, and I'll walk you through what that means. You all know by now what Evo Robo is, right? We are evolving robots over phylogenetic time, or over evolutionary time. And for any one robot in this population of evolving robots, evolution is sculpting or changing the neural controller of that robot, or maybe even changing the body, which changes the sensor-motor coordination of the robot, right? The robot acts, it does something, it gets some sensory repercussions from that actions, it does something else, and around you go. So we've been looking, in all the experiments so far, we've been looking at two different time scales. What happens from one time step to the next in the bullet physics engine? How is the robot reacting to what it senses? A very short time scale. And then we've been looking at a much longer time scale, right? We just looked at that fitness curve on the previous slide. How are things changing over evolutionary time? But of course, as always, in nature, things are much more complicated than that, right? We do not just change from second to second as you're reacting to immediate sensory stimulation. We are also part of a very long-scale evolutionary process. But there are also important dynamics that are going on at the intermediate scale over your lifetime, right? None of us were born in the form that you find yourselves today. There are important changes that have occurred to your body and your nervous system over your lifetime or over the ontogenetic time scale, right? The developmental time scale. So we've been looking so far at Evo-Devo in this course. And I'm going to show you a set of experiments I conducted a few years ago, which is Evo-Devo Robo. I'm going to show you a robot that changes its body plan in the physics engine. So at the end of the simulation of a single robot, that robot's body plan is different from its body plan when we first put it in the simulator. And that ontogenetic trajectory, that change over the robot's lifetime, that developmental program itself is going to change over evolutionary time, right? So Evo-Devo is short for a branch of biology known as the evolution of development. Evolution does not act on static bodies and brains. What evolution is really doing in nature is tinkering with a developmental trajectory. How does a single cell split and split again and split again in a particular way to produce all the variety we see in nature, right? So biology has given us Evo-Devo. We're going to again apply that now in robotics, and I'm going to show you why you would do that, right? As you've all experienced now, an evolutionary robotics experiment is a pretty complicated thing. You've got a lot of things that are going on in your simulation now. Why the heck would we want to introduce yet another biological detail and make our evolutionary simulations even more complicated? This is something that, as an evolutionary roboticist, we often come up against. Why are we going to all this effort to make these complicated biological simulations? So today I'm going to show you an experiment we designed to try and really answer this question. I'm going to show you that by adding in the Devo, we make our system more evolvable, right? Like we just saw in the previous slide, if you have the right genotype to phenotype mapping, you can make it easier for evolution to evolve better robots over time. Today I'm going to show you that if you add in Devo in the right way, you can also make things easier for evolution. Okay, so I'm going to, as we go forward now, I'm going to use phylogenetic and ontogenetic quite a bit. Just remember that phylogenetic means the population of robots is changing from one generation to the next over evolutionary time. Ontogenetic is I'm talking about one robot and how that robot is changing over its lifetime. Just a little bit of etymology. Phylogenesis. So genesis is the birth of, or the creation of, or the coming into being of. Phylo is tribe or race, or when we're talking about biology, species. So phylogenetic is sort of how species come into existence over time. For our purposes today, we're going to just think of phylogenetic, obviously, as one species, our population of robots changing over time. Ontogenesis, so again, genesis or birth of, onto being to be or to exist, right? So how an adaptive agent comes into being or comes to exist over its lifetime. Okay. I'm going to maximize the screen here so I can play the videos for you today. Okay, so let's introduce this idea of Robo, Evo, Devo. And we're going to think today about the Devo part as a form of scaffolding. So we've talked about scaffolding a number of times in this class. What is scaffolding, generally speaking? The training wheels example, right? So scaffolding is a common tool in the toolkit of roboticists and also the toolkit of parents and teachers, right? You're observing a learner, the learner's having a hard time. How can you make the environment easier for the learner to start to get their mind around the basics of the task? And then once they start to demonstrate some competency, you gradually start to remove the training wheels. So we can actually think about development itself as a form of training wheels. How would this work? Well, I'm going to show you, we're going to look at a bunch of different experiments today, some that are just Evo Robo and others that are Evo Devo Robo. So let's start with Evo Robo that we're pretty familiar with. And of course this worked before class started and now it's not working. To make things tricky because I got a lot of videos to show you today. Can I play this? No. Let's try this again. Can I share the screen? Mirror displays, yes. No such luck. Okay, we're going to do this the old-fashioned way. Okay, so standard evolutionary robotics experiment. We're going to evolve, in this case, our quadruped over here, and the fitness function is approach the target object as closely as possible. So not maximizing displacement, but minimizing distance to an object. Not that different from what we've seen before. What you're seeing in this video here is the initial random population of neural controllers. So the standard evolutionary robotics experiment, we fixed this quadrupedal body plan and we're evolving the synaptic weights of the artificial neural network. That's our random population. And after a little while, we get this. Back to the Ministry of Silly Walks, right? Not the most efficient quadrupedal gait you've ever seen, but gets the robot to the target object. This should not be unfamiliar to anyone in this room. Okay, now I'm going to add in the Devo part. It's going to be exactly the same, more or less the same robot. We're going to continue to evolve the neural network of the robot like we did before. Fitness function is exactly the same. But now, over phylogenetic time, the robot is going to change its infant form into its adult form. So there's going to be a little bit of ontogeny in here. And I'll show you as we go. So let's start with the initial random population. So you can already see the difference at the starting point here. We're going to start with a robot that is not upright, but is lying flat. The forelegs are arranged horizontally, but the neural controller is still the same. We're just evolving it to approach the target object. You can sort of see the random controllers here.
When we say we're changing this over phylogenetically,
Yes.
what do we mean?
So when I say we're changing this over phylogenetic time, so the artificial neural network is always changing over phylogenetic time. From one generation to the next, we have a population of neural networks. They're being mutated and crossed and slowly changing over phylogenetic time. That's always the same. That's the Evo part. What I'm going to show you in a moment with these videos is that the body of the robot is also going to change over phylogenetic time.
So are we working with phylogenetic time in our own?
You absolutely are. That's right. So if you're using the hill climber, you really only have a population with one individual in it, right? In most of the experiments we've looked at in this class, you have a population of multiple robots, but it is phylogenetic time, right? So you're going from one generation to the next.
So if putting it close to the ground allows it to develop a neural network that then when we make it a new, going along the Devo when it's standing up and it's better, right? That's very much like based on nature. Like we start off crawling and then we're walking. But
Exactly.
how can we get an intuition for that kind of Devo process for other problems? Like, if we're thinking about the virtual, like make images thing.
Right.
Like what's
the
process?
Devo there? So that's an excellent question. So you're anticipating the end of this lecture, and that's fine, right? So as you can probably imagine at this point, the Devo we're going to introduce for legged locomotion is not unlike the Devo that we experience, right? Which is you start close to the ground and gradually stand upright, which makes sense for a task like locomotion, right? That's the scaffolding. But what would be the scaffolding for object manipulation or sensing affordances or anything else that you want to evolve? That is an open question, but we'll talk about some ideas for that towards the end of this lecture. Okay, hold on to that one. Okay, let's look first though at exactly how this works. Okay, so what I just showed you in this video was the initial random population. Now I'm showing you just one evolved solution that evolves in the population after a very short period of time that gets to the target object. At this point, the experiment is not done. We're assuming that in both cases here, without development and with development, we want to evolve a neural controller for an upright four-legged robot. So in the case down here where we're going to add in Devo, which we haven't quite seen yet, the robot is not upright, it lies flat. So at this point, the developmental program is constant, which is the robot throughout its lifetime stays flat, right? So this would be the equivalent of a human being that never learns to stand upright, always crawling around. So at this point, we're going to treat this as phase one of the evolutionary experiment. When we finally evolve after a few generations, after a little bit of phylogenetic time, once we evolve a robot that manages to crawl to the target object, so we get a fitness value that's above some threshold, we now go in and change Devo. We change the developmental program. And then we unpause evolution. Evolution is just going to continue doing what it was doing in the previous phase, which is evolving the synaptic weights of the neural network. But now that neural network is going to be controlling a slightly different robot. This is going to be a robot that starts flat, and as it's moving around, it gradually stands upright. Okay, here we go. So it starts flat. As it's walking, its legs are gradually becoming more vertical, and it still gets to the target object. So what happened here? Well, we started with our initial population of random controllers. We evolved them for a while until one of the neural networks in the population got this robot, the one that always lies flat, to the target object. Pause evolution, introduce this change to the robots, replay all of the neural networks in this population at this time, and what do you think happened to the fitness of all of the ANNs in the population when they were suddenly dropped into this slightly different robot?
They fell.
They fell, right? The neural networks that were evolved for this robot have never experienced a robot that actually stands upright. And if you watch this video, you can sort of see the robot falling over right towards the end of the simulation. Okay, as I said, I'm going to show you a lot of videos today. These are all in the tarball that's pointed to from the schedule. So if you want to go back and watch these at your leisure, you can do so. Okay, so imagine we have all of these ANNs. We replay them in the new robot. Fitness drops, but it only drops a little bit, right? Because the robot started flat, which the ANNs are familiar with, but over the lifetime of one robot, over the ontogenetic time scale, things became increasingly unfamiliar to the artificial neural network. So fitness dropped a little bit, but evolution just carried on, and we continued evolution until we got this new robot that now, or we got this new neural network that now gets the robot back to the target object, right? So over phylogenetic time, the average fitness in the population is going up, 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 up. One of the ANNs manages to get the robot to the target object. All of the ANNs are replayed in this slightly different robot. Fitness drops a little bit. We continue evolution. Fitness goes up, 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 until we get an ANN that, again, succeeds at the task.
So how gradual does the change have to be kind of considered Devo? Like, would Carl Sims' experiment be Devo because he started out with these swimming robots and then bought them on land?
So the Carl Sims experiments with the virtual creatures was all Evo-Devo.
Yeah, Evo-Devo.
Because there was no, or sorry, it was Evo-Robo. I'm sorry, okay. Evo-Robo. There was no Devo,
okay.
Right? There was change over evolutionary time.
Okay.
Evolved robots for swimming,
yeah.
And then threw them on land.
Yeah.
But during the lifetime of any one of Carl Sims's creatures, it didn't experience change. It wasn't swimming for the first half of its lifetime, managed to get on land, and then adapt how it was moving on land, right? That would be, so Devo is always change during a single lifetime, right? Everything we've seen up to this point has been Evo-Robo. Yeah? Okay, questions so far? All right, so let's have a look at these little cartoons here. So I'm going to show you a lot of videos, but eventually I'm going to run out of patience and we're going to switch to the cartoons. That's what the cartoons are here for, right? So as you can probably figure out, each one of these panels is meant to depict Devo, the ontogenetic change, right? So imagine we're looking from behind or from the front of the robot. The robot starts lying flat. And the inset axis here, this is representing the horizontal axis of the inset axis here, is representing the lifetime of the robot. So this is the first time step of simulation, 2, 3, 4, all the way to the 1,000th time step in the simulation, right? One lifetime for one robot. The dotted line represents the height of the center of mass of the robot. What's the average height of the robot? And obviously a robot that stays flat throughout its lifetime maintains a low center of mass, right? When we get to here, we're now changing the developmental program. So now the developmental program, the legs start horizontal and gradually rotate vertically throughout the lifetime of the robot. And so over its lifetime, its center of mass increases. Yeah? So this axis here is phylogenetic time. These little axes in here show ontogenetic time. And as you can see, the ontogenetic trajectory, or the way the robot changes over its lifetime, changes over evolutionary time. Okay, you're all physics engines gurus by now. How did we do this? How did we simulate, how did we allow evolution to evolve locomotion for the robot? And how did we, on top of that, manually force the robots to go through these different developmental trajectories?
So perhaps like at every modulus of a large time step number equals 0, make the angle at which all the legs are tilted a little bit like that, but stop once you get to 90 degrees.
Close. That's close to what we do. So we could have shared control of a single hinge joint by changing the joint offset and then allowing evolution to do what it does. To make things simpler, to make things more continuous, so things were changing at every time step.
Okay.
The shoulder of the robot, if you watch carefully, is 2 hinge joints. So one that allows rotation forward and back, and the second hinge joint dictates swinging inward and outward from the body. We took control of this hinge joint, and we basically set the desired angle of this hinge joint to change very slowly over the 1,000 time steps of the simulation. And the second hinge joint, this one, that was just controlled by one of the motor neurons from the artificial neural network as usual, right? So evolution is controlling this, and we're controlling this. So far, so good? Okay, so now we're at phase 2 of this one evolutionary run, and you sort of get how this game goes now, right? Once we get this robot that exceeded this fitness threshold, we now changed the developmental trajectory again. Now we're going to start the robot with legs angled 45 degrees downward, and they're going to gradually, over the robot's lifetime, rotate from 45 down to 90 down, and the ANN is still controlling the second hinge joint as normal. Okay, so here we go. Okay, starts at 45 degrees. The legs start at 45 degrees, and they become increasingly vertical. The robot got a little stuck at this point. The fitness threshold was actually pretty forgiving in this case, so this actually counted as success. It's okay. So now we've evolved a robot that manages to get close to the target object with this developmental trajectory, pause evolution again, and now in the 4th and final phase, we make the last change in development, which is the robot starts with its legs upright and maintains upright legged locomotion throughout its lifetime. Again, Ministry of Silly Walks, right? Not the ideal quadrupedal gait, but good enough. Okay. So now we have 2 very different experiments here. We have Evo Robo up here and Evo Devo Robo down here. And as good roboticists now, you should all be thinking, why add in this additional complexity, right? Professor Bongard better have a pretty good reason for putting that in. And I do, I promise you. The main advantage here is that we were able to evolve upright legged locomotion faster, so with less generations overall, than in this case. Why? Tyler?
When the robot starts lying flat, it sort of has less degrees of freedom. It's easier for it to learn how to make the motion to move itself forward.
Yep.
Without kind of falling over, worrying about that.
Jeez. Okay. Tyler, you were telling us why Evo Devo Robo.
Right. So it's
Has an
easier
easier
for
start.
it to learn how to move forward when it's lying flat. It doesn't
Right.
have to worry about falling over and whatnot. And then you slowly, after it's kind of learned how to do that, then you slowly increase the complexity and make it stand up more so it has that more complex behavior, but it already knows how to sort of move forward, so it can slowly learn that.
Exactly.
But I had a question
Sure.
also.
Sure.
Do you think it would evolve even faster if instead of making these kind of jumps of how you change developmental time to slowly, so in like the first time step, have it flat, but then like at each generation, make it start just a little bit more standing up?
Exactly, right? So this is a question that all parents come up against, right? So do you just take the training wheels off the bicycle, or do you find a way to do it more gradually? Okay, so to unpack what Tyler was saying, it's not actually the case that the robot has fewer degrees of freedom here. There are still the same degrees of freedom. What is different when the robot is lying flat is that the fitness landscape is smoother. So if you go back and look at lecture 4 or 5, when we talked about evolutionary algorithms, the way to think about what evolution is doing is it has a population of solutions to a problem, which in our case are robots. Those points exist on a landscape, and the height of any point is the fitness. Mutation represents a new point which moves horizontally relative to the parent, right? So moving horizontally in a fitness landscape means your genes are slightly different from the parent. A big mutation means you move a long distance horizontally, and a slight mutation means you move a small distance horizontally. Evolution will only work if you have a smooth fitness landscape. Right? So if you're here and you produce these offspring, they should have similar behavior and similar fitness to you, right? Their heights should be not that different. If you do, and that's why the hill climber is called a hill climber, right, is eventually through enough mutations, you can reach the top of a hill, right? So when you're lying flat, the fitness landscape is pretty smooth because even a new individual which moves slightly different from the parent, it's going to shuffle a little bit further. It's going to shuffle a little bit faster, a little bit slower than the parent. In legged locomotion, when you're upright, the fitness landscape tends to look a little bit more like this, right? You might have a parent that manages to take 1 step or maybe 1.5 steps. Any mutation is probably going to cause the robot to fall over, right? So very difficult for evolution to make progress on this kind of landscape because even if you manage to be climbing a local slope, you're not necessarily getting anywhere, right? You'd have to have a lot of solutions that manage to find the uppermost point, right? Any change you make when you're here, you're likely to make a big drop, and there's only a little bit of space for you to make improvement. So that's why the Devo here is called morphological scaffolding, because the morphology or the body plan, depending on how the body plan is put together, can make the fitness landscape smoother or rougher. What's happening on the Evo here, so as we're gradually forcing the robot to stand upright, is these points are moving around in this space, and this space is becoming rougher and rougher. The surface itself is changing. But as the landscape is changing underneath the population of robots, evolution is still getting them to climb the slope, and so they're more likely to get to the top when the fitness landscape finally congeals and is as rough as it's ever going to get. Make sense? Okay. Back to Tyler's other question. Why do this in 4 discrete jumps? Why not have 5 phases or 10 phases, or make it continuous where the robot is changing very slightly over every generation? We could have done that. We just sort of did this arbitrarily. That would be an interesting thing to investigate, right? So now we've entered new territory where we're asking questions about Devo. We're asking questions actually about Evo-Devo. How do we allow Devo, or the developmental program of the robot, to change over evolutionary time?
So, would we also, like, going off of this, could we also, like, add new limbs and joints, like how much can we change the morphology?
Okay. Again, you're anticipating me, so we're going to actually
Just look ahead in the lecture.
we're actually going to add limbs in a moment. We'll get there. We'll get there. Okay. Before we get there, so back to scaffolding. We've actually looked at scaffolding a number of times already in lecture. This is probably not going to play for me now, right? Well, you probably remember this video here. We started by placing the blue block right in front of the robot. It evolves the ability to grasp and lift it. Every time it successfully evolves the ability to do so, we move the blue block 1 millimeter further away. And same thing, right? We start with a relatively smooth fitness landscape. It's easy for evolution to evolve grasping. Very hard from scratch to evolve the ability of walking towards an object, grasping it, and holding on to it while you lift that object onto your back. Yeah. We looked at passive dynamic walking, right? Evolve a robot that can walk downhill and then gradually decrease the slope until eventually it's walking on flat ground. This is another interesting paper in the field which we haven't had a chance to talk about. This was a paper that was written right at the beginning of physics engines. This was a pretty impressive paper in and of its own right. It started with a biped robot, so very unstable walking. At the beginning of evolution, whenever the robot started to fall over, they applied a compensating force. So these arrows here, these are almost literally training wheels now, right? As the robot starts to tip over, they detect the orientation of the robot and apply a force pushing in the opposite direction. And those external supporting forces are gradually made weaker and weaker and weaker over evolutionary time until at the end they're not there at all. So for those of you that are working on legged locomotion or tasks that are pretty unstable, you might consider using this force assist trick. Okay. These are all, however, environmental shaping or environmental scaffolding, right? There's something outside the robot that we're changing. We're changing the robot's environment in all of these cases. Here, what we've been talking about is morphological scaffolding. It's the robot's own body which is making things easier early on. Okay. So here we go. We're going to now switch from videos to cartoons, and I'm going to show you a whole bunch of experiments. This is a mouthful here, but the panel A here is basically representing Evo Robo, right? So I'm going to use physiological change, so that means the robot's body is changing. No physiological change in this experiment, right? Just evolve controllers for the upright legged robot. The second experiment that I'm going to show you here, there's going to be phylogenetic parametric change. So phylogenetic change, you look at the body is changing over evolutionary time, over generations, but there's no ontogenetic change. Within the lifetime of any one robot, its body does not change. I'm calling this kind of physiological change, I'm now going to call it parametric change, because there's one parameter or one number that dictates the angle of the legs relative to the body, right? The parameter is equal to 0, the legs are flat. If the parameter is equal to minus 90, the legs are vertical, minus 45, and so on, right? So there's a parameter that we're using to tune the robot's body. The third experiment is the one that I showed you the 4 videos of. We have phylogenetic change. The robot starts lying flat and eventually is upright. And we also have ontogenetic change. During the lifetime of the robot, it starts lying flat and becomes upright over the lifetime of the robot. Right? That's the one we've seen. Okay, so still parametric change, right? One number that controls the angle of the legs relative to the body. Okay, so now back to Slayton's question about adding legs. We're going to, in the 4th experiment, now look at a different kind of body change, which is topological. So topological meaning that the topology of the body itself is going to change. We're going to start with a robot that has no legs. It's just a worm robot. And we're going to add parts to the robot as we go. And as you can imagine, we're going to add legs. Okay, here we go. So we have phylogenetic, in the fourth experiment, we have phylogenetic change. The robot starts legless at the beginning of evolution, and by the end of evolution, it has legs, but no ontogenetic change, right? During the lifetime of any one of these robots, it doesn't change its body. In the fifth and final experiment, we're going to put all of these things together. The robots are going to experience topological change. They're going to start as legless robots, and they're eventually, again, going to become upright-legged robots. We have ontogenetic change. The robot is going to start legless, and during its lifetime, is going to grow legs that are increasingly long and increasingly vertical. That ontogenetic change itself is going to change over evolutionary time. It's going to transition from the legless to the legged form faster and faster and faster until at the end it's born, quote unquote, in the upright legged form. So we have 5 different evolutionary experiments where we're introducing more and more Devo as we go. Okay, I'm going to show you a couple videos from the last case, from the 5th experiment, before we look at results. Okay, here we go. Any luck? No. Okay. Okay. We have a legless robot, and over its lifetime, it grows increasingly long and increasingly vertically aligned legs. You'll notice also that it's a hexapod, not a quadruped. So to make things even more confusing, we have these 5 experiments that we did with the quadruped. We did all 5 experiments again with the hexapod. We wanted to see whether Devo was useful not just for one kind of robot, a quadruped, but for a different kind. Okay, again, you're all physics gurus, physics engine gurus by now. How do you grow body parts in Bullet? A little bit of physics engine black magic here.
Are you like literally swapping out like one body for a longer body?
We've tried that in the past. So at every time step or every couple time steps, you could delete an object and add it. That doesn't work very well because the physics that's being computed under the hood by the physics engine relies on momentum, right? So what was the acceleration and forces from the previous time step? So if you suddenly remove something, you mess up the physics calculation. So you can't cheat by deleting and adding objects, but that was a good idea. It was something we tried initially, doesn't work.
Is it possible to set the length a bit longer and then move the position of it in relation to the body a bit farther, like over time?
That's the trick, right? So you can't change the geometry of an object in Bullet once you've placed that object in the physics engine. So what we actually did in this case is inside the body of the robot, we placed a cylinder, and I'm just going to do the right leg for you. The right leg was attached by a linear joint, so like a piston, which can extrude things or retract them. And then over the lifetime of the robot, we actuated the piston. So in essence, it was extruding the right leg out of the right side of the body.
It's like a telescope.
It's like a telescope, right, exactly, something that's being extended outward. The linear joint is attached to a hinge joint, and the hinge joint is attached to another hinge joint, which gives you this and this, right? So there's actually two objects, one that's being extruded right out of the right side of the body, and the other one that's being extruded left out of the left side of the body. And we use the same trick about gradually rotating the legs downward. So you can grow structure in a physics engine if you do it carefully. Yeah? Okay, so this is the fifth experiment, right? Topological change, the robot starts with fewer pieces and adds pieces as it goes. And let me continue on with these. Second phase, the robot transitions from the legless to the legged form faster. So these legs are extruded faster, and the robot reaches the upright legged form in the first 2/3 of its lifetime. In the third phase, it goes from this legless to the legged form even faster over the first third of its lifetime, and then maintains the upright legged form for the last 2/3 of its lifetime. Manages to miss the block, but close enough for our purposes. And then finally, we throw away the original legless form altogether. So Evo, Devo, Robo. Evo, Devo, Robo. Okay, so that's the 5 experiments. Let's actually look at some results now.
When you threw out in the
Yep.
last one,
Yes.
when you threw out, you just had it standing up, was it depending on anything that happened in the past?
That's a very good question, right? So what is happening during this final phase of evolution, right? In these last generations of the evolutionary run, evolution is just doing what it's done during the rest of the evolutionary run, which is tuning the synaptic weights of the neural network. So is it relying on anything that happened previously? Sure, right? This robot here reached the upright legged form in the last 2/3 of its lifetime. So any controller, any neural network that managed to get this robot to the target object has some experience with successfully orchestrating the movement of these legs towards the target object, right? But it's slightly different because it hasn't had to do it over the entire length of the simulation, right? That's the whole point of Devo, right? The scaffolding. We're gradually removing the training wheels over evolutionary time.
What would happen if we took the final controller and just made it have weird legs?
Right, what would happen
Is
if
it
we
more-
changed...
Is it more adaptive now? Like, would it have the, because it has all, presumably it has all that, all the processes from when it was like crawling around
Yes.
45 degrees. So if we just threw it a curveball and gave it like 45-degree legs, would it do well? Would it do well with 45, 90, you know?
Right, exactly. So that's actually called an atavism, which actually occurs in biological organisms. What happens if there's a mutation or something that goes on that brings back some trait from the past? So horses, which have the single hoof, from time to time horses are born that have 2 small hooves or 2 toes off the side because horses used to have 5 toes like we do, right? So from time to time there's a throwback to earlier forms. And as you would imagine, there's some residual memory, quote unquote, again, in the nervous system to be able to orchestrate movement with that earlier atavistic form. So yes, we are going to throw some curveballs at these robots, again, in a few slides' time. So hold on to that thought. Okay. All right, here we go. So the quadruped robot, we're just going to look at the first 3 of the 5 experiments first. No physiological change, which corresponds to the light gray bar. Phylogenetic parametric change here, which is the dark gray bar, and the black bar here is Evo-Devo Robo, right? Change over the body of the robot, and that change itself, the change occurs over the lifetime of the robot. But we're only looking at the moment at the parametric case, where the legs become increasingly vertical. We'll look at the topological change in a moment. For each of these 3 experiments, I did 100 independent runs. So the results that you're looking at here are the result of 300 independent runs. And what I measured was how many robots had to be evaluated until finally the upright legged robot got sufficiently close to the target object. If we just do Evo Robo, it takes about 5,000 robots to do so. If we introduce phylogenetic parametric change, it takes a little bit longer, actually. And if we introduce Evo-Devo Robo, it takes even longer to do so. So we got a little bit nervous at this point because the results we were getting was the opposite of our hypothesis. Somehow Devo was making things harder for Evo, not easier. This little cartoon here shows that the initial simulations we did was we placed the target object directly in front of the robot. So the turning angle that the robot had to make was 0. All it had to do was go straight. So we continued on and did some more runs where now we started to move the target object. We started to place the target object front and left. So the robot had to walk and turn left towards the target object like you saw in all the videos I've shown you so far, right? So now we have 300 runs here, another 300, so 600, 900, 1200, 1500 total evolutionary runs. And now things start to seem to be changing. Now Devo seems to be helping. It takes less time to evolve controllers for the final upright robot when we introduce Devo compared to just Evo. Why? Why did this turn things around?
It's doing less work. Like it's already had, like if you just throw in Evo to do a very complex problem, it's going to be very difficult. Like you don't, sorry.
That's all right. Other ideas? So Devo seemed to make things worse here. Devo seemed to help here. What was it about these slightly two tasks? Why is it that walking forward and to the left, in the case where the robot had to walk and turn somehow to the left, that Devo helped? So if you're running full speed forward and suddenly you have to start running to the left, what happens? You're going to try and make a tight turn. You're going to start to tip, right? So if you need to move, and you need to move and turn at the same time, it actually makes you less stable. Remember our discussion about legged locomotion? You're trying to keep your center of mass more or less over your feet. It becomes a harder thing to do when you're walking and turning because your center of mass tends to get pulled to the outside of the arc that you're making as you turn. So when you have to walk and turn, the fitness landscape actually becomes rougher. It's harder to maintain your balance when you need to walk forward and to the left than if you just need to go forward. You can actually see this if you look at the light gray bars. They tend to go up here, right? So things are getting harder if we just evolve upright legged locomotion for turning. So far, so good? Okay, let's keep going. Now let's introduce experiment 4 and 5, which is where we introduce topological change. So now the body change that the robot is going to experience, or the physiological change that the robot is going to experience as it goes from the legless to the legged form. We put Evo-Devo in again, which are the light gray bars. So the light gray bars over here are exactly the same as the light gray bars over here. So we have experiment 1. Now we have experiment 4 for the dark gray bars and experiment 5 for the black bars. What's going on now? And same thing, we did another 300, 600, 900, 1200, 1500 runs for evolving robots to go straight forward and to go forward and go to the left. What's happening now? So again, we saw the same sort of thing when the robot had to go straight forward. Devo wasn't helping, was making things worse for us to force it through these 4 phases than just to allow evolution to start with the upright-legged robot. At the end here, though, now things look a little bit different. This actually made things harder for evolution. You can see the dark gray bar is higher than the light gray bar. Why is that? Let's just start with that for a moment. Why is this form of Evo-Devo Robo more difficult than just Evo Robo?
Is it because it like has to relearn kind of how to get to the location?
Exactly, right? So we evolve controllers here that work for a worm robot and manages to get to the target object. Once one of the controllers gets the worm robot to the target object, we pause evolution, put these legs on that the controllers have never seen before, right? And the controllers can control these legs. What do you think happens, right? Whatever worked before probably is disastrous here, right? So it's not just a slight drop in fitness, it's probably a complete drop in fitness. And as you mentioned, evolution is probably starting all over again with this. Once it does manage to get this robot to the target object, now suddenly it's exposed to robots that have longer legs. Now, whether this is as traumatic for evolution as this one was, I don't know, but you could be pretty sure that this one was pretty traumatic, right? So adding development can help, but it also can hurt.
So why is adding ontogenetic make things so smooth? Like it's about the it's a very similar difficulty.
Smooth as in the smoothness of the fitness landscape?
No, I'm talking about the amount of time it takes to solve the problem at various points. Like
Okay.
it seems much more constant than the other two.
Yes, right. So if you look at the light gray bars, and in this case the dark gray bars, they go up over time,
Yeah.
or not over time, they
No.
go up as the environment changes,
Yeah.
which is walking further and further to the left, right? Which is difficult. So it's hard to evolve forward-legged locomotion. It's even harder to evolve forward locomotion and turning. It's easier to fall over if you're walking and turning for these robots at their speeds.
Could the fact that the addition of ontogenetic change, the gradualness of which their bodies change, could that help in the falling over, because it already kind of has some scaffolding for when it was just 45 degrees. So now when it's tipping, it knows what to do?
Yes.
Not-
When it's
I mean,
tipping, does it
it's-
know what to do?
It's hard to I don't want to put personify this too much, but it's not going to just freeze up, maybe.
It's hard to say, right? Because we're not looking at any one evolutionary run or any one robot. We're looking at summary statistics across a lot of evolutionary runs. So it's hard to say what it was about the scaffolding that helped when the scaffolding was removed a little bit. But presumably it did, right? Because now when we look at experiment 5, now it's really making a difference. So the little asterisk that you see up here, we conducted a statistical test, and these 100 runs really did solve the task in less time than these 100 runs. Here it looks like this took less time than this, but we can't quite be sure. The statistical significance isn't quite there. Between this pair of bars, for sure, we can be sure that Evo-Devo Robo helped. Right? So it didn't help here because we're changing the body over phylogenetic time, and suddenly the controllers have to deal with something they've never seen before. But that doesn't occur in this experiment. In this experiment, the robot starts legless and grows legs over its lifetime. So the controllers in this population have experienced a robot that has upright, long, vertical legs. It only experienced them for the last few time steps of the lifetime of the robot, but the controllers have seen that case before and managed to keep the robot upright for long enough to get it to the target object. So now, in phase 2, when we accelerate the change from the infant to the adult form, these controllers that survive from this evolutionary time into this evolutionary time have seen, quote unquote, these different forms of the robot's body. It's much of a more gradual transition from here to here than it is from here to here, and so on. Okay. So those are the 5 experiments for the quadruped. We did the same thing again now for the hexapod. So here's the hexapod with the parametric change. And for the hexapod, things were even more significant. Actually, it was already helpful even when the target object was right in front of the hexapod. So adding Devo to our Evo Robo experiments, it can be helpful not just for the quadruped, but for the hexapod. We don't know if this is a general property, but at least for these 2 different robots. And again, now with the hexapod, when we force the robot to grow legs over its lifetime, now we're really seeing an advantage here, right? We can solve the task with many fewer robot evaluations than if we didn't include Devo. And again, we see experiment 4 actually making things worse, not better. Okay, so that's the why of evolving morphology, right? If we just fix the robot's body, which is the light gray bars, and evolve controllers for those bodies, we may, unbeknownst to us, be actually forcing evolution to solve a very difficult task. If we build a biped robot and say, okay, evolution, evolve walking for this biped robot, it may be very difficult for evolution to do so. So why not allow evolution to start with a more forgiving body plan and then gradually move that body plan to the actual one we want, which is the biped or the quadruped or the hexapod. So there's an advantage here in terms of speed. We can evolve things faster in some cases with Evo Devo Robo than we can with just Evo Robo.
Couldn't this just be a function of how we measure fitness? So ontological change, we start with the thing that it already kind of knows how to do, and it does it fairly well, but the ones that change a little bit over time, so say it's going from 0 to 45, so it already knows how to do things at 0 pretty well, so it goes a bit. And then the ones that can do things at 45 a little bit survive a little more, so, but if we...
Right, which the fitness function rewards.
Which the fitness
if
function
you fall
rewards,
over, that's it, right?
But if, and that's why it's better to have the slow change rather than just the steps.
That's right.
But my question is would it be possible for us to change our fitness function to reward not just getting closer, but also to, I guess that would be a lot more work, but reward it for
being closer to the final target
type. Yeah,
Yep.
exactly.
Okay, that's a great question. That's something that we're working on at the lab at the moment.
Okay.
Which is you get fitness for getting to the target object, and you also get some fitness points
For
being closer to the final robot in which the controller is going to be placed, right?
Okay.
Then we can throw away this manual approach, and coming back to something Tyler said, then we don't have to do things from one phase to the next. We can just have a whole population of creatures, some which are more legged, some which are slightly less legged, some which are closer to the ground, some are not, their center of masses are lower, some of them their center of masses are higher. Evolve that, right? So be more quadrupedal and be more closer to the target object at the end. Okay, in the interest of time, I'm gonna carry on. So, as I said, we did this experiment to try and demonstrate to our fellow roboticists and to engineers in general that we're not building some biological detail, in this case Devo, into our experiments because we just like biological things and we want to make our experiments more biologically realistic. We're doing it for a real practical reason. As you all know by now, evolution takes a while, right? So we want to do whatever we can to make things easier on evolution so it can make faster progress. Turns out, when we had done this, we then tried to throw a curveball at our robots to see how adaptive they were. So I'm going to go back and forth between these 2 slides so you can see the difference. We took all these, 1,500, 3,000, all of these I forgot, what was it, 300, 600, 900, 1,200, 1,500, 3,000, 6,000 evolutionary runs. From each of the 6,000 evolutionary runs, we took the best robot out of the population, which gives us 6,000 evolved, successful robots, 6,000 robots that are all upright. It's the final form, and they all get to the target object. We replayed those 6,000 robots in the simulator, but now we perturbed them. So this was like the big dog experiment. We kicked the robots as they were walking by applying slight random external forces to the robot. And as you can imagine, when you apply these forces, the robot, it's upright, it's legged, and it usually falls over before it gets to the target object. So we measured the percent drop in performance. So if we have one robot that manages to get this far, we play that robot back in the simulator, and we kick it, and it only gets this far. We look at this percent drop in performance. So in this case, about 33%. That's what's plotted on the vertical axis here. On average, in each of these sets of evolved robots, what was the drop in performance? And the lower the bar is, the better, because we want a lower drop in performance in response to these perturbations. So in essence, the lower the bar is, the more robust the robot is to external perturbations. And as you can see in most of the cases here, the black bars are lower than the light gray bars, which is kind of surprising. Again, if I go back and forth, it took us less time to evolve a more robust robot. This goes against the basic idea in the field, which is if you want a robot to be robust, you have to evolve it to a lot of different situations, which takes longer. So up until this experiment, it was basically understood that in robotics, there was a trade-off between speed and robustness. The more robust or more adaptive you wanted your robot to be, the more optimization you had to do against more and more environments. The introduction of Devo here, at least in these experiments, we don't know about in general, in these experiments, it breaks the trade-off between robustness and speed. We evolved robots in less time, and those robots were more robust.
Do you know the time difference on these?
The time difference is measured in the number of robot evaluations.
Yep.
It took us to evolve a controller that got the upright legged robot to the target object. So it's not speed here measured in seconds, it's speed here measured in the number of robots that needed to be evaluated to get there.
Oh, I see, these are part of the same thing.
Yeah.
Two sets.
That's right, exactly. So this is the result of evolution. This is showing the robustness of the evolved robots or the evolved controllers. Yeah? Why does Devo break this antagonism? How is it possible to get something that's more robust with fewer robot evaluations?
It already dealt with those multiple situations on the way to getting there.
Ah, okay. We never kicked the robots while they were evolving, so it never actually experienced these external forces. So what gives here?
Didn't experience the external forces, but it was subject to more change in the forces of experience.
That's exactly it, right? So most of the controllers in the black bars here or the ancestors of those controllers, if not those controllers themselves, had to control robots that were flat, upright, no legs, some legs that were half as long, which means there was probably a much wider range of forces that those controllers experienced. Those controllers don't experience the forces directly. All they experience is what are the sensor values and what should I do in those situations. So those controllers probably saw a wider range of different sensory signals and managed to maintain upright legged locomotion in those. So in essence, Slayton, you were right that the previous experiences of the controllers prepared them for now not an internal change to the body, but external changes being exacted from the environment.
Do they perform better on, so if you push a robot, right, and it goes down a bit, you could argue that, like it being shifted this way, you know, it kind of is like when it was at a lower angle and it has stuff to deal with that. But if we just flip it on its back, would we see more robustness?
Probably not,
Probably
right?
not.
So there are perturbations to which it's not going to be robust. Okay, I'm sorry we've run a little bit over. You have a quiz due tonight and you're working on the screenshots for deliverable 2, right? Or sorry, for milestone 2, I believe. Okay, thank you very much. We'll see you on Tuesday. Tyler, are you heading back to Farrell Hall?
No, right.
You got a class, huh? Okay, all right. Sweet. Do you have a class?
Oh, I don't.
Can I talk to you about that? Sure. No.
Am I being late? Because I swear to God.
What's that?
Is it about lateness? Because I swear
No,
to
no,
God.
that's fine, that's fine. So as I mentioned, we have a camera crew here today. They're shooting some images for promotional material for UVM for next year.
Yeah.
Would you be willing to come back to Carroll with me? They want you to get some pictures with a student and that sort of thing. Do you
Yeah.
mind doing that?
No, not at all.
Thank you very much. All right, let me just pack up here and we'll head back.